All right, so this video we're going to focus on heat transfer and heat capacity, so how we use heat capacity and specific heat capacity in calculations. So by the end of this video, we're going to be able to quantify, using some calculations, the relationship between heat transfer, Q, and temperature change, delta T. Now, as we're doing this, we want to think, what are the equations that we're going to utilize? We're going to use these two equations here, Q equals Cm delta T and C delta T, to quantify the heat transferred between two objects that are at different temperatures. We want to be able to understand the applications of how we use the first law of thermodynamics, reminding us that that is the law of conservation of energy. So we're looking at energy being conserved as we are going to have that energy be transferred. So now again, we're going to use these two relationships, Q equals Cs M delta T and Q equals C delta T. And reminding us these are both conversion factors, our specific heat capacity and our heat capacity, between how much heat is transferred and our change in temperature that we're looking at. So when we're looking at this, is always, whenever we're looking at this, an object that undergoes a change in temperature. So we're looking at something that changes temperature, and it's going to release or absorb heat as it undergoes that temperature change. Now, we're going to work through a couple examples, and then I'll give you a chance to practice this on your own. So here what we have is a ceramic mug that has a heat capacity of 77.5 joules per degree Celsius. So let's go ahead and think about, what does that mean? Our heat capacity is going to be 77.5 joules per degree Celsius, and that is for all of that ceramic mug. So it's not per gram, it's for the whole thing. And then what we see here is that we then add boiling water, 100 degrees Celsius, to the mug, and the temperature of that mug changed from 25 degrees Celsius to 85.3 degrees Celsius. So we see we have an increase in temperature here, and it reached thermal equilibrium, and thermal equilibrium is where the temperature of the mug and the water are going to be the same. So now as we look at this, let's answer some qualitative questions before we actually do any calculations here. The first one we want to answer is, what lost energy in the form of heat? And we think of something losing energy in the form of heat, that's the thing that decreased in temperature. And so that would mean our water lost heat. It lost energy in the form of heat, so it gave away kinetic energy. And the mug then is going to gain that heat in the form of energy in the form of heat. So when we look at this, what does that mean with regards to the signs that we should calculate? The Q for the water should be negative. Again, that's because we lost energy, lost heat. And then the Q for the mug should be positive because it's gaining energy or gaining heat as we transfer that heat from one object to the next. Now we connect this back to some of the previous things that we've talked about, the molecular kinetic energy for the water. So the water went from 100 degrees Celsius down to 85.3 degrees Celsius. Its temperature decreased, which means its average kinetic energy decreased as well, because we know that those two are directly proportional to each other. Now the amount of kinetic energy that it lost is equivalent to the heat that's transferred. So now let's get to the quantitative portion of this. So we want to calculate the Q of the mug after the water and the mug have reached thermal equilibrium. So again, we're assuming no heat loss to the surroundings, just heat transfer from the mug to the water or the water to the mug when we're looking at our heat being transferred here. So we go ahead and we see, well, we want to find the Q of the mug. So again, we use these two possible circumstances, Q equals C delta T or Q equals MCS delta T, or specific heat capacity. We can again use either one of these, but what we notice is that we already know the heat capacity of the mug, which is 77.5 joules per degree Celsius. And so now as our mug is going to increase in temperature, it's going to absorb heat based upon that heat capacity. So it probably makes sense for us to use our first relationship here, Q equals C delta T. So our Q is going to be equal to our 77.5 joules per degree Celsius times our temperature change. So we ended at 85.3 degrees Celsius. We started at 25.0 degrees Celsius. And so what we notice is that the Q of our mug should be positive, which makes sense because we notice here we have an increase in temperature when we're going from 25 to 85.3 degrees Celsius. We would get positive 4.67 times 10 to the third joules. So that's the amount of energy that was gained by the mug as it increased in temperature. Well, then we want to connect this back to, well, what's happening to the water? So we want to calculate the heat capacity of the water added to the mug. So again, if we're going to use heat capacity, we're probably going to use this first relationship that we just mentioned, the heat capacity of the water times our change in temperature. Again, we're not trying to find the specific heat capacity, we're just trying to find the heat capacity. But in order for us to know what our heat capacity is, because we do know what our temperature change is, we know our initial and final temperature, we got to be able to know what the Q of our water is, so how much heat the water gained or lost. Well, we bring that back to something we've already identified. We already know the Q of the mug. And so we think, how do these two things relate to each other? And so this is applying the first law of thermodynamics. Whatever amount of heat gained or lost by one object is equal and opposite to the heat lost or gained by the other object. So we can make this a little bit more specific here and say the Q of our mug is equal to the opposite of the Q of our water. And so if we know the Q of our mug is 4.67 times 10 to the positive third, that would tell us the Q of our water is the opposite side of that, negative 4.67 times 10 to the third joules. So that's the amount of energy that the mug took or stole or was transferred from the water. That's the heat of our water. Well, now we know the amount of heat that was lost by the water, so we can go ahead and plug in the information that we know to solve for our specific heat capacity. Negative 4.67 times 10 to the third joules equals the heat capacity of our water times our change in temperature. Final temperature, 85.3 degrees Celsius. Our initial temperature, 100 degrees Celsius. And we would go ahead and we quickly divide that over, and we would get the heat capacity to be 318 joules per degree Celsius. So now we know the heat capacity of our water. So the whole sample of water, it would take 318 joules to cause it to change in temperature by 1 degree Celsius. Now finally, we notice that maybe there's something else that we have the ability to identify, the mass of water in the mug. And anytime what we know the identity of our substance, that tells us that we know the specific heat capacity, because that specific heat capacity is something that is a characteristic or property of that substance. So water, specific heat capacity would be 4.184 joules per gram degree Celsius. So for every 1 gram of water and every 1 degree Celsius, it takes 4.184 joules to make that change occur for that 1 gram. Now when we think, how do we connect this back to some of the information that we've already talked about? Well, let's connect these two equations that we have here. Q equals C delta T and Q equals M specific heat delta T. We notice that these are both relationships between heat and our temperature change. And so what we see here, if we're talking about the same substance, we'll see that our heat capacity is equal to the mass times the specific heat capacity if we're dealing with something that is a pure substance, like we have here, water. So that means if I know what my specific heat capacity is and I know what my heat capacity is, I can go ahead and maybe rearrange this a little bit, and we find that our mass is our specific heat capacity divided by our specific heat capacity. So we now have the ability to plug in the information that we know, 318 joules per degree Celsius for our heat capacity, 4.184 joules per gram degree Celsius for our specific heat capacity, and we would find that we would have 75.9 grams of water. So now we found the mass of water that we have present inside of the mug that we poured it into there. And again, we think of the major tools that we used. we know that we have these two relationships that we have the ability to quantify. Again, this is for us to quantify heat transfer. And we also know one really important other tool that we have, the heat gained or lost by one object that it transfers heat to is equal and opposite to the object that it comes in contact with. This idea of the law of conservation of energy, or the first law of thermodynamics. So now what I'm going to have you do, why don't you go ahead and pause and check your understanding of what we just talked about. So I'm going to go ahead and read the question, and then why don't you go ahead and pause the video and answer the question on your own. So you have a hot copper pan at 240 degrees Celsius with a mass of 1.18 kilograms. Into this copper pan, we add 355 grams of olive oil at room temperature, so 25 degrees Celsius. What will be the final temperature of the oil after the system reaches thermal equilibrium? And we also have some information about our specific heat capacities. Now down here, I just have some guiding questions that might help us think about answering this question. So why don't you go ahead and pause the video now, answer this question on your own, and then after you're done with that, come back and look at how possibly I worked through this specific question. Now that you had a chance to pause the video and work on this on your own, hopefully we got to a solution that the final temperature is 109 degrees Celsius. Now let's talk about how we got there. So first thing that we have is we have this idea that we have a transfer of kinetic energy, or this idea of heat, from what is hot, our pan, to what is cold, the oil. So we have this transfer of heat. Now, as we're looking at this transfer of heat, we want to look at this idea that, well, those values are going to be equal and opposite to each other. So this is again the idea of the law of conservation of energy. Well, let's make this a little bit more specific to the example that we have, right? We're going to quantify our heat using one of those two relationships that we've identified so far. Now, before we do that, we also want to make sure we make it specific to how much heat is being transferred from the copper to the oil. So let's go ahead and make that specific to our example here. So the Q of the copper is going to be equal and opposite to the Q of our oil. Now again, it doesn't matter which side I put this negative on. I could put it in front of the copper if I want. It doesn't matter. We're just saying these values are equal and opposite to each other. Now once we've identified one of these is going to gain heat, one's going to lose heat, and we know that those will be equal and opposite to each other, the next step is we want to figure out for each of those, how are we going to calculate those values? Are we going to use Q equals C delta T? Are we going to use Q equals MC delta T? Well, again, we know the identity of these substances, and they're pure substances. They're not mixtures. And because of that, we have the ability to use these specific heat capacities that we know. So we could say the Q of our copper is going to be equal to the mass of the copper, the specific heat of the copper, and then the change in temperature the copper undergoes. Likewise, we know the Q of our oil is going to be equal to the mass of the oil, the specific heat of the oil, and the change in temperature the oil undergoes. Well, now what we see here is that we have a bunch of information, and we say, do we know all this information? Well, we say, yeah, we know the mass of the copper is 1,180 grams, 1.18 kilograms. Now, why do we think we're going to use grams? And that's because our specific heat capacity is 0.387 joules per gram degrees Celsius. And then we say, well, do we know what our temperature change is? Well, we don't actually know what our temperature change is because we don't know what our final temperature is. But maybe let's expand this out a little bit and say the change in temperature of our copper is going to be our final temperature minus the initial temperature of the copper, which is 240 degrees Celsius. So now we notice in our expression here, we now really only have one unknown, our final temperature, if we were to plug all that information in. We go back to our oil, and we notice that we have 355 grams of oil. We know the specific heat capacity of oil, 2.01 joules per gram degree Celsius. And again, we don't know what our temperature change is. However, we do know that our change in temperature is going to be, again, our final temperature minus the initial temperature of the oil, 25 degrees Celsius. So now we have, again, one expression. Now to remind us, between those two, that is the same final temperature. And the reason for that is we've reached thermal equilibrium. So we could say that those are the same final temperatures. So now our last step is where we're actually going to plug in these expressions to each other, because we don't actually need to know the absolute value of how much heat is gained or lost by the copper and the oil. What we do know is they're equal and opposite to each other. So let's go ahead and plug that information in, and then we can solve for our final temperature. So we have 1,180 grams of copper. Our specific heat capacity, 0.387 joules per gram degree Celsius. Our delta T is our final temperature, minus 240 degrees Celsius. And again, we put this negative sign out front. So we're going to put that negative out in front of our copper there. That's going to be equal to the expression that we set up for the oil. 355 grams of oil. Our specific heat capacity, 2.01 joules per gram degree Celsius. And then the temperature change, final minus our 25 degrees Celsius. So now we notice we just have to do a little bit of algebra. I'm not going to go through all those steps, but once we go ahead and solve for that, we're going to get a final temperature of 109 degrees Celsius. So now hopefully this gives us a good thought process as we are working through these heat transfer examples. We always want to start with this idea of transferring heat from one object to the next. Our next kind of step is figuring out how we're going to quantify those. Then we go in and we identify what knowns and unknowns do we have. And in this case, the only unknown is our final temperature of the oil and the water, which are the same. And then we will go ahead and we relate those two to each other.